Hello everyone, my name is Ruyu Liu. Today, I will be presenting my project on the hybrid optical radio frequency communication channel model, and my supervisor is Professor Su Wai Ho. The presentation includes 5 parts. I will start with a brief introduction to the background, then detail the dataset, the models, and their performance, and a conclusion in the end. Now, let's move on to the first part. First, I'd like to introduce the title of my project. As the name implies, it combines two wireless communication channels, radio frequency and free space optical. In the early stages, radio frequency transmission, which uses radio waves, was the predominant method. However, as the demand for higher data rates grew, free space optical communication emerged as an alternative. But both radio frequency and free space optical are really affected by weather conditions. Just so you know, for convenience, I will refer to radio frequency as RF and free space optical as FSO from now on. Nowadays, to achieve more reliable signal transmission, we use a hybrid communication system. In this setup, signals travel between location 0 and location 1 via both RF and FSO links. During transmission, power loss known as signal attenuation occurs. The goal of my project is to develop a model that predicts signal attenuation in this hybrid system. To achieve this goal, we first develop independent models for RF and FSO attenuation separately, focusing on how different weather conditions affect each channel. Then, we build a joint model to study correlations between the two channels. Now, let's move on to the data part. The dataset I used is based on real synthetic empirical data from a hybrid communication system operating in 6 cities worldwide. It contains around 90,000 measurements, with 2 main output variables. In addition, it has 25 weather-related features, like temperature, humidity, visibility. After exploring the data, we found that RF attenuation follows a stable, nearly normal distribution, suggesting it's more stable in different weather conditions. Meanwhile, the distribution of FSO attenuation is right-skewed, typically low with occasional extreme values, which means it is higher sensitivity to environmental factors. For categorical features, one is the CNOP code representing 7 different weather conditions. It's pretty imbalanced, with clear weather and rain making up most of the data, while conditions like fog, snow, and dust storm appear much less often. For continuous features, if you look at the heat map on the right, you can see some strong correlations between them. All of this points to some redundancy in our features, suggesting we might need feature selection before we build our model. Now let's take a look at the models we constructed. I used a random forest approach for this regression task, because they can handle both continuous and categorical variables, and work well with high-dimensional data. However, they can be heavily influenced by strongly correlated features. Remember, in the background section, to meet our project goal, we first built independent models for each channel. since both two channels are heavily influenced by weather conditions. So we focus on the weather conditions feature synop code. That means for each channel, we split the dataset into 7 smaller subsets, one for each weather condition, and train a separate random forest model on each subset. We call this our specific model approach. We also built a generic model by treating the synop code as a single categorical variable and training one random forest model on the entire dataset. As I mentioned during data exploration, our dataset has some highly correlated features, which can cause random forests to overfit. So, before building each random forest, I perform feature selection to avoid that issue. I use a wrapper method with backward elimination, which can be a bit involved, so here's a quick overview. I'm using the FSO generic models feature selection as an example. First, we include all available features in the model. Then, we train a random forest and measure its performance using RMSE and R-square. Next, we identify and remove the least important feature by OOB information. Here, Ri, rain intensity, is the least important feature. So, if we remove Ri in the first round, we retrain the model without Ri and record the new RMSE and R-square. And then remove the least important feature in the current model again. Now it's SC synop code. We keep repeating this process, removing one feature at a time until there are no features left. By looking at the order in which features are removed, you can easily tell which ones really matter. We see a clear turning point marked by the green dashed line, where RMSE suddenly jumps and R-square drops. Features removed before this point are considered unimportant, while rows returned afterward are viewed as important features. Summing up the process for the independent models. For both RF and FSO channels, I built one generic model and 7 specific models. Then, for each dataset, I apply feature selection to get a refined new dataset containing only the most important features. After that, I train a random forest on each new dataset and tune key hyperparameters to optimize our models. Now that we've covered the independent models, let's move on to part 2, the joint models. You might wonder why we need a joint model if we already have separate models. The key reason is to study how these two channels correlate under different weather conditions. For example, if rain knocks out the RF channel, does it also knock out the FSO channel at the same time? If both channels broken together, the entire system is useless. But if one channel stays robust, while the other is affected, the system can still function. In the independent models, we build models separately. In the joint model, we use a chained approach. First, we train a random forest to predict RF attenuation using the Euro weather features. Then, we take that predicted RF attenuation and add it as a new feature in the dataset. With this updated dataset, we train another random forest to predict FSO attenuation. We can also reverse the process by first predicting FSO attenuation, then predicting RF attenuation. Alright, after all the hard work building our models, let's check out how they actually perform. These are the metrics I use to evaluate my independent models. I will not go into the math in detail, but if you are interested, feel free to check out the formulas. In short, a lower RMSE and a higher R-square mean the model is performing better. We use the Pearson correlation coefficient to measure the linear relationship between the RF and FSO attenuations. Its value ranges from -1 to +1. When the value is close to 0, we see the correlation is weak. Now let's compare the independent models. We tested two kinds of independent models, generic and specific models across different weather conditions using RMSE and R-square. From the figure, you can see that the RF channel generally has a much lower RMSE than the FSO channel, which means it's more stable under various weather conditions. The FSO channel, on the other hand, is more sensitive to extreme conditions like dust storms, which shows up as big jumps in RMSE and drops in R-square. Both channels see worse performance when there's a dust storm, but specific models do slightly better than generic models. Under showers, generic models beat specific model for both channels. That shows how generic models can use data from other weather conditions to handle those with less data more effectively. Apart from dust storms and showers, both models perform similarly. But the generic model's simplicity and consistent reliability, especially when data is limited, make it our best choice. Now let's compare independent models and joint models. In this chart, triangles represent negative correlation values, while squares represent positive ones. The green symbols shows the actual measured correlation between RF and FSO under different weather conditions. Meanwhile, the red and blue symbols indicate the correlations predicted by the independent and joint models respectively. As you can see, the blue symbols represent joint model are generally closer to the green ones, suggesting the joint model does a better job of predicting how RF and FSO correlate. So we consider it the better option. Finally, let's make a conclusion. In this project, we developed random forest models to predict signal attenuation for hybrid communication system. We explored two main approaches, independent and joint models. For the independent models, we compared generic and specific models. We also include feature selection and hyperparameters tuning to optimize the model. Based on the RMSE and R-square. While specific models showed slight advantages under certain extreme conditions, generic models proved more reliable overall and remained competitive across most weather scenarios. Additionally, we built a joint model to capture correlations between RF and FSO. By incorporating the predicted attenuation of one channel as a feature when modeling the other. After comparing the Pearson correlation coefficient between the measurements, the independent model and the joint models, we found that the joint model more accurately mirrored real-world channel interactions. Overall, we built a joint generic model to predict signal attenuation for hybrid communication system. That's all my presentation. Thanks for listening.